In this video, we'll expand our understanding of the idea of computation itself by discussing an introduction to the concepts of data representation and binary numbers. Recall that computational thinking is about breaking down complex problems into manageable parts, recognizing patterns, abstracting away unnecessary details, and designing step-by-step solutions that a computer can execute. That is, in computational thinking, we're formulating our problems in such a way that we can use a computer to follow a deliberate and detailed process to automate our solutions. One fundamental aspect of this is understanding how data is represented in such a way that a computer can process it. Everything you see on a computer, texts, images, music, cat gifs, even this video, ultimately needs to be stored in digital memory. But computers themselves have no concept of sound or light. They don't understand what a cat gif is, nor even a cat. So how do they store all of these things that they don't even understand? Somehow, all of this information needs to be represented in a format that the computer does understand. What computers do understand is power. I don't mean that in the socio-political sense, but in the sense of electricity. Computer memory can be thought of as a long sequence of tiny electrical switches that rely on voltage levels to represent data. Voltage in memory uses just two states, high and low voltage, representing the values 1 and 0 respectively. Each cell in memory is effectively either on or off, 1 or 0. This simplicity makes computer memory incredibly reliable and efficient, but it means that computer memory can only ever just store those two numbers, 1 or 0. Because of this, all digital data, whether numbers, text, images, or sound, must ultimately be represented as a series of ones and zeros. To understand how computers do this with all kinds of information, let's start with something familiar. Base 10 or decimal numbers. These are just the normal numbers we're used to using. In base 10 or decimal, we have 10 unique symbols with which to represent things. These are the digits 0 through 9. Side note, the word digit literally comes from the Latin for finger, which tells us probably why humans love to use base 10 as our default numbering system. But the choice to use 10 different symbols is an arbitrary one, as we'll see in just a minute. So anyway, in base 10 we have 10 digits, but obviously we can represent more than 10 different numbers with these digits. There's an infinite number of numbers. So if we wanted to represent the next number in sequence after 9, we would just spill over into a second digit or a new column. We put a 1 in the new column and reset the current column to 0 to represent the next number in our sequence, and then we count up from there. This is what's known as positional meaning in numbering systems. By putting a second column, the same digits become worth 10 times more than the digits in the first column. So in order to represent bigger and bigger numbers, we can add more and more columns. For example, the number 3456 in decimal means 3 1,000s plus 4 100s plus 5 10s plus 6 1s. Okay, so hopefully nothing new here so far. Binary numbers aren't much different. With binary numbers, also known as base 2 numbering, we have only two unique symbols. So each binary digit, or bit as they're called, can only have the values 0 or 1. There are no other symbols in binary, so if we wanted to represent a number larger than 1, we need to use more bits. Just like in base 10, or any other numbering system for that matter, we have positional meaning, so bits in new columns are worth more. So if we wanted to count in binary, we can count to 1 pretty easily. But after that, we need more columns, more bits. Notice that after 1 in binary comes 1 0. In binary, 1 0 does not mean 10, instead it's the binary equivalent of 2. It means 1 in the second column and 0 in the first. Similarly, 1 1 doesn't mean 11, it means 3. So with 2 bits, we have 4 different possible combinations, so we can represent the numbers 0 through 3. But then we filled up these two columns. So next, as you might guess, we add another column. Notice that since we have fewer unique symbols, just 0 and 1, we need to use more columns or more bits to represent the same numerical idea as we did in decimal. Notice also that each time we add a new column or a new bit, we can represent twice as many combinations. All of the old values with that bit set to 0, you can imagine leading zeros here, and then again with that new bit set to 1. So with 3 bits, we can represent 8 different possible values, or the numbers 0 through 7. We add another bit. Again, we double the size of the values that we can represent, and now we can represent 16 values. After that, again, we spill over into a 5th bit, and we can continue counting up from there. With decimal numbers, each new column lets us represent 10 times more numbers, and so each new column is 10 times larger than the previous column. We go from ones to tens, then hundreds, then thousands, etc. In binary, it's the exact same idea, except each new column is 2 times larger than the previous column. because we're counting in base 2. So we go from a 1's column to a 2's column, to 4's, to 8's, to 16's, to 32's, etc., etc. In general, we can say that each new column is the base times larger than the previous column. Another way to say that is that each column is a power of the base. So in decimal, we have 10 to the 0, which is 1, 10 to the 1, which is 10, 10 to the 2, which is 100, 10 to the 3, which is 1,000, etc., etc. In binary, it's the same system, but our base is 2. So we have 2 to the 0, which is also 1. We have 2 to the 1, which is 2, 2 to the 2, which is 4, 2 to the 3, which is 8, 2 to the 4, 16, 2 to the 5, which is 32, etc., etc. So for example, in binary, the number 1011 represents 1 in the 8's column, 0 in the 4's column, 1 in the 2's column, and 1 in the 1's, which equals 8 plus 2 plus 1, or 11 in decimal. Ultimately, binary and decimal numbers are just two different ways of representing the same thing, the same numerical concepts. Converting between these two numbering systems lets us express numbers in a way that we understand, while allowing computers to store and process those same numbers in a way that they understand. A useful analogy to help with understanding binary is counting with bags of jelly beans. Imagine you have a row of bags with jelly beans in each, and each bag holds twice as much as the last one. So we have a bag with 1 jelly bean, a bag with 2, a bag with 4, 8, 16, and so on. Each bag can either be opened or closed. When you open a bag, all of the beans spill out, meaning it either contributes all of its beans to our total or nothing. There are no partially open bags. Now ask yourself, if you had these bags of jelly beans in front of you, which ones would you open to make a pile of exactly 11 beans? No more, no less. Could we start with a bag of 16 beans? No, obviously that bag would be too big. 16 is greater than 11, so that would overshoot our goal. The next one down has 8 beans, so we can start there. So we open that bag, and now we have 8 jelly beans in our pile, and we need to find 3 more beans to get our goal of 11. If we want 3 beans, we wouldn't open the bag of 4, because again, that's too big. So we leave that closed and move on to the next largest, which is 2. 8 and 2 makes 10 in our pile, so we need 1 more bean in order to get our goal of 11. So we can open the 1 bean bag, and then we get to our goal. In this analogy, opening a bag corresponds to putting a 1 in that column, and not opening a bag means putting a 0. So 11 in binary would be 0, 1, 0, 1, 1, with or without the leading 0. Let's try it again with a target of 26. So 16 is less than 26, so if we open that, we need 10 more. That means we can open the 8, which leaves 2 more. 4 would be too much, so we can skip the 4. We can open the 2, and that gives us our goal, so we don't need to open the 1 bag. We can leave the 1 bag closed. So to get 26 jelly beans, we need to open 1 bag of 16, 1 8, and 1 2. What this is showing is that we can represent all the same numbers as we did in decimal, but now using powers of 2. The pile of beans left on the table will be the same size, regardless if you label it as 26 or as 11010. The size of the pile doesn't change. That is, binary numbers are just another way of representing the same numerical information. Briefly, if we were to use bags of jelly beans in base 10, our bags would hold powers of 10, and we would have the option of opening up to 9 bags of each size. But again, we can represent all the same size piles of jelly beans. So to get a pile of 26 beans, we'd open 0 of the hundreds, 2 of the tens, and 6 of the ones. This jelly bean metaphor also hints at a simple algorithm for converting from decimal numbers to binary, which recall is what we'll need if we want to store our decimal numbers in computer memory. To convert from decimal numbers to binary numbers, we can follow a simple step-by-step process known as a greedy algorithm. It's the same process we just used to count out jelly beans. It's called a greedy algorithm because at each step in our process, we're going to take the largest possible move towards our goal. That is, we'll open the largest bag of beans. This isn't the only algorithm that will solve this problem of going from decimal to binary, but it is an algorithm that does so and is relatively easy to follow. So our algorithm starts with some input, that being the number that we want to convert, given to us in decimal. So we'll call that x. The first step then is to find some large power of 2. This will be the leftmost column of our binary number. We saw before that we can start with the largest power of 2 that's smaller than or equal to our target number. But the way this pseudocode is written, any power of 2 bigger than our input will do. We'll just end up with some leading zeros if we pick a number too big. So we pick some large column, like let's say 32, And then the algorithm proceeds to repeat a bunch of steps. So until we've reached our goal, repeat the rest of all of this. We check if our target is greater than our current column, meaning there are fewer jelly beans in the current bag than our goal. If so, we mark a 1 in that position and subtract that column or power from our target. That is, we open the bag. If x is not greater than y, so if there are too many beans in the current bag, we put a 0 for that column and we just move on. That is, we leave the bag closed. In either case, we've checked this column, so we shrink down to the next column by dividing the current column by 2 to get to the next. And then we repeat those steps. If we put a 1, then our target, x, will be a smaller value this time because we subtracted the beans that we opened. So as we keep repeating, our target's going to get smaller and smaller, and eventually it will reach 0. And every time through this loop, we're dividing our column, the value y, by 2. Notice that this is the same process we just followed when we were opening bags of jelly beans, except now it's written out in a more detailed step-by-step manner. So let's try following this algorithm's steps out and validate that it works as we expect. So let's open up a notepad and follow along with this algorithm, just step by step here. So for example, to convert the decimal number 42 into binary, so we'd say our input starts as the value 42. Now, the next largest power of 2 that's greater than 42, so we have powers of 2 are 1, 2, 4, 8, 16, 32, 64. So 64 is the smallest power of 2 that's greater than our input. So we'd say x is a decimal number, so we could say x is 42, and we could say y is our starting column, which is 64. Okay, now it says until y is less than 1, we want to repeat. So y is 64, so we don't stop yet. And the next line says if x is greater than or equal to y. So if x is 42 and y is 64, then that's not true. Here x is less than y. So we come down to this otherwise part, and it says output a 0. So we'll make an output section here. We'll say output, and so far we put a 0. Then the next line says divide y by 2. So we go back to y and we say 64 divided by 2 is now 32. And we go back to the top of the loop. Y is still greater than 1, so we continue. It asks, is x greater than or equal to y? 42 is greater than 32, so we follow these steps, and it says output a 1. So we come down to our output section, and we put a 1, which is now under the 32's column. The next line says subtract y from x. So if y is 32 and x is 42, that means x becomes 10. And now we're left looking for 10 more jelly beans. Down at the bottom there, it says divide y by 2, so go on to the next column. So y becomes 16, and we repeat. So y is still greater than 1, 16 is still bigger than 1, so we keep going. Is x greater than or equal to y? X is 10, y is 16, that's not true. So we jump down to the otherwise part here. 16 is too big, so we put a 0, and we divide y by 2 again. So we put a 0, and we divide y by 2, making 8. Back to the top, it says, is x greater than or equal to y? That is true. So we say we output a 1 in the 8's column, and we subtract y from x. So y is 8, x is 10, so x becomes 2. We divide y by 2, and continue. Is x greater than y? That is false, so we put out a 0, and divide y again. And we go back up to the top. Y is still greater than 1, so we're still repeating. And it says if x is greater than or equal to y. So in this case, they're equal, so that's true. So we output a 1 in the 2's column. Subtract y from x, which puts us at 0. We divide y by 2 again, which leaves us with 1y. 1 is not less than 1, so we loop again. So with x is 0 and y is 1, x is less than y, so we do the otherwise section there. We put a 0 in the 1's column. We divide y by 2 again, which gives us 0.5 or 1/2. At that point, y is less than 1, so we no longer repeat, which means we're done. So our final binary representation of 42 is 10, 10, 10, with or without the leading 0. I recommend you pause the video and try following this algorithm again to convert your other favorite numbers as well. Try to validate both the flow of the algorithm as well as your understanding of it. And welcome back. Now hopefully now you're convinced that for any decimal number, there's a corresponding binary number that we can use to uniquely represent it. If we want to convert the other way, from binary back to decimal numbers, like for example when retrieving information back out of computer memory, the conversion is actually quite simple to do. In fact, we've already seen how to do it. To get the decimal value of a binary number, we can just multiply each bit by its corresponding column and sum the result. For example, given this large binary number, we can express it as a summation of its column values. So since there's a 1 in the 128ths column, we say 1 times 128. But since there's a 0 in the 64 column, we say 0 times 64. But notice that we're only adding the column values where the bit is 1, so we can actually just omit the columns where the bit is 0. Then if we sum the remaining columns that have 1s, we get our final decimal number. We can describe this process as an algorithm as well, and here is one such example pseudocode algorithm that will take you from a binary input to a decimal output. But I'll leave you, the viewer, to verify the details of this one. Now, these conversions form the basis for how computers store numbers and perform calculations. When working with computers, though, it's rarely necessary to do any of these conversions ourselves. But in order to understand computation, it helps us to know that this is happening in the background. That's it for this quick introduction to the binary numbering system. In the next video, we'll go over how computers use binary numbers to represent all kinds of data. Take a break or don't, and I'll be waiting in the next video.